Hi, and welcome back to the LIGA Learn Introduction to Functional Programming course. In this module, we will learn all about polymorphism and type classes. We will begin the module by discussing what is known as parametric polymorphism, and then move on to looking at the difference between something called kinds and types. Then we'll look at type classes, a very important topic within Haskell. We look at type class hierarchies, and then take some time to focus on the numeric type classes in the hierarchy. Following this, we will look at how you can provide default implementations in your type classes and automatically derive instances for them. Finally, we will compare parametric polymorphism with ad-hoc polymorphism and do some exercises in using type class constraints in function signatures. We have lots of exciting things to cover in this module, so let's get started. Let's say we want to write a function which, when given an argument, just returns the argument back. Ignoring the type signature, how exactly would we write that function? Well, here is a function which we have called in-out, and it does exactly that. Whatever you call the function with, the value is returned. And as you can see here, when we call the function with any type, it will return the value that was passed in. Here we are calling it with a string, here we are calling it with an integer, and here a double. And here is a bool. And everything works as expected and the value is returned. The question is, what exactly is the type of this function? Well, let's ask GHCI what it thinks the type is. When we ask for the type of this function, it says it is of type A to A. Now what exactly does this type signature mean? Notice how it is a lowercase being used for the type name. Every example we have seen so far has had the type name start with an uppercase letter. Concrete types always start with an uppercase letter. For example, string, int, and all of the custom types we have defined so far. However, a type name beginning with a lowercase letter in a type signature actually represents a type variable. This means it could be any type. The type is said to be a type variable because the type varies depending on the type of the argument of the function when it is called, like we can see here, where the types of the arguments are string, integer, double, and bool. And so the type signature becomes string to string on this function call, because it takes a string and returns a string, and then int to int on this function call, and so on. Type variables can be given whatever name you would want. For example, we could have given the function this type signature, or we could have given it this type signature. Neither of these type signatures actually improve the situation compared to the simple A to A type signature. So since longer type variable names don't actually improve readability of the code, we usually just give a type variable a single character name like A, B, C, or D. One thing that you should definitely note about the A to A type signature is that the same type variable is used as the parameter type and the return type. This puts the restriction on the function that whatever the parameter's type is, it will be the same as the return type. A function which contains type variables in its type signature is known as a polymorphic function. Polymorphic literally means of many forms, which makes sense here since we are talking about functions which will work with any type. And so this can be read of as, for any type A, in-out takes in an A and returns an A. There is already an inbuilt function which is defined in the same way we have defined in-out. That function is called ID. You can see the type signature for ID matches the one we see for in-out. Let's explore a few more built-in polymorphic functions. There is the FST function, which is pronounced first. It takes a tuple of type A and B and returns A. Take a second to think about what you think this function actually does. If you said it returns the first value of the tuple, then you are right. Let's take a look at this type signature. There are two type variables, A and B. Type A could be anything and type B could be anything. The type A is the type of the first parameter in the tuple and the type of the returned value. And so, this acts as a sort of constraint for the values that can be returned. The first value in the tuple and the return value of the function must have the same type. The type B can be anything. There are no constraints in the signature, so it could even actually be the same as type A. We can call the function like so. Here, in the first invocation, the types of A and B are the same. They are both strings. In the second invocation, they are different. A is an integer and B is a string. Another inbuilt polymorphic function is SND, pronounced second, which has the following type signature. You can probably guess from the type signature that this just returns the second item in the tuple. and here are some example usages of the second function. Two more examples of polymorphic functions in the Haskell Prelude include head and tail. These are polymorphic functions which act on lists. Both functions expect you to pass in a non-empty list and will throw an exception if you pass in an empty list. Head takes a list of A and returns an A. It extracts the first element of the list and returns it, as you can see here. Tail takes a list of A and returns a list of A. Tail returns all of the list except the head. In other words, it returns all of the list except the first element. Since these functions throw an exception if you pass in an empty list, they are not really used in production code, but they are good enough for learning, so we will be using them quite a bit. When you have a type variable in a type signature, it is known as a form of parametric polymorphism. This is because the type variable is kind of like a parameter in the type signature. Let's understand this further by focusing on the ID function. We know that the type of the ID function is A to A, meaning it can take any type and will return a value of the same type. Now when we call the function with a string, it returns the string like we expect. In the case of this function call, since we know the parameter is of type string, we can conceptualize the type signature for this particular function call actually being string to string. At the time of the execution of the function, it is as if the type variable A in the type signature is given the value of string. It is the same when the function is given an int. You can think of A as being an int in that case, and so on for any other type. Hopefully now you understand what we mean by parametric polymorphism. Parametric because there is a type parameter, and polymorphism because the function has many forms, one for every possible type. You will see parametric polymorphism everywhere in Haskell, and so you will get used to it quite quickly. In a previous module, when we were discussing algebraic data types, we saw how we could define our own custom types, and we made a distinction between the type constructor and the data constructor. If you remember, I used the example of a dateTC type, and I explicitly named the type constructor dateTC and the data constructor dateDC to make the distinction between the two clearer. We saw that we could view the data constructor like a function, which takes in parameters, in this case 3 ints, and returns a value of the type. Just like the data constructor, the type constructor too can take in parameters, but so far every type constructor we have seen has not taken any parameters. This has been on purpose to keep things simple. I mentioned in the previous module that we would eventually look at type constructors which take parameters too. That time has now come, and we are going to cover that topic over the next few minutes. One of the simplest examples of a parameterized type is the maybe type, which is defined in the standard prelude. It is defined as maybe A equals just A or nothing. As you can see, the type constructor has a type parameter, which we have named A. The type constructor parameter, which is declared on the left of the equal sign, is available to use as a type parameter to any of the data constructors defined to the right of the equal sign, which is what the just data constructor does. It takes in a type of A. The nothing constructor is a nullary constructor. It does not take in any parameters. Let's take a minute to see how we can create values of the type maybe. In this case, we are creating two values, m0 and m1. Both of these values are declared with the type of maybe_int. Remember, in the type signature, we refer to the type constructor, and when creating values, we refer to a data constructor. In this case, the type constructor does not share its name with any of the data constructors, and so it is easy to see what is being invoked. But in other cases, they may share the same name, so you should be aware of the distinction. Type signatures refer to type constructors, and to create a value refer to data constructors. The value of m0 is set to nothing, and m1 to just 43. Nothing does not take a parameter, and so we can create its value by simply invoking the constructor. However, the just constructor has a type variable as a parameter. The type will always be the same as the type passed into the type constructor, which in this case is an int. So when we call the just constructor, we must pass it an int. In the next examples, we are creating three values, m2, m3 and m4, all of which have the type maybe string. m2 and m3 are invoking the just constructor with a string to match the type in the type signature, and m4, just like m0, creates a value of nothing. Now if we inspect the types of the data constructors in GHCI, we can see that the type signature for the just constructor takes an A and returns a maybe A. This is just as we would expect, since the just constructor has a single type parameter of type A. The type signature of the nothing constructor takes a maybe A directly. Now this could potentially be confusing. The nothing constructor itself does not take a parameter in its definition, but then how come when we ask for the type it does? Since the nothing constructor does not use the type parameter A, it effectively does not matter what the type A actually is. Regardless of the type of A, the nothing constructor can be invoked to create a value of type maybe A. The nothing constructor returns a polymorphic value, and so without any explicit type declaration, Haskell will infer the most generic type, which is maybe A. If we provide a more specific type declaration, then the type of the nothing value will be more specific. For example, M0's type is maybe int, not maybe A, and M4's type is maybe string. What exactly is the point of the maybe type? Well, the point is to have a type which indicates the absence of a value as well as its presence. Let's say you want to write a function which returns the first item in a list. Well, the list could be empty, so we could write the function so it returns a maybe of A. Then when the list is empty, we return a nothing, and when it is not empty, we return a just with the value of type A. This is a lot safer than what is in the prelude by default, which is what we have seen before, where an empty list would cause the function to throw an exception. Let's take a look at another parameterized type, the either type. The either type is also defined in the prelude. In this case, it takes two parameters, A and B, and there are two data constructors, the left, which takes a value of type A, and the right, which takes a value of type B. The point of either is to have a type which can represent a value with two possibilities, either left or right. In most cases, it is used to represent either a correct value or an error. The right constructor is used for the correct value. This is because right has the double meaning of the direction right and the correctness right. The left constructor is used to hold an error value. Let's look at a function which returns an either. Here, we are defining a function called int_div, which takes two ints and returns an either of the string int. The type parameters to either have been given here as string and int, which means the value of the type parameter to the left constructor must be string, and the value of the type parameter to the right constructor must be an int. The point of the function is to perform integer division. That is, take two ints, divide the first by the second, and return the result truncated to the closest downward int. We isolate the case where we are trying to divide by 0, by pattern matching on 0, and return a left result, because it is an error. In this case, we just return a string indicating the reason for the error. And then for the general case, we return a right result, containing the value after performing the actual integer division, using the inbuilt div function. The types of the constructors are exactly as you would expect. Both left and right take a single value and return an either. One of the things you should know is that the A and B type parameters can actually be the same. So you can have an either string and that would be perfectly fine. But when they are different types, as is the case for the int_div function, then the left constructor is constrained to take a value of type A, and the right constructor is constrained to take a value of type B. The left constructor completely ignores the B type parameter, and the right constructor completely ignores the A type parameter. This is similar to what we saw before with the nothing constructor. When it comes to types, we have already seen some polymorphic ones without realizing, tuples and lists. We haven't realized it because they come with their own special syntax in Haskell. For lists, the square brackets act like a constructor, and so we can ask GHCI what its type is. And we get told that the empty list is of type list of A. The empty list is kind of like the nothing constructor for a maybe. Any type parameter value is valid, since an empty list is a valid value for any type of list. And so just like for nothing, Haskell will show the most generic type for the empty list, which is the polymorphic value of list of A. For tuples, the comma acts as a constructor, and so we can ask GHCI what its type is. So a single comma takes a value of type A, and a value of type B, and returns a two-tuple of type A and B. And when we have two commas, it takes a value of type A, a value of type B, and a value of type C, and returns a three-tuple of A, B, and C, and this goes on for the rest of the tuple sizes. That's pretty much it for now for our discussion on parametric polymorphism. We are now going to take an aside here and talk about a topic which is not really that important for beginners, but I think will be useful for you to know so that you can understand more about the Haskell type system, and that topic is kinds. Suppose we have a function called intDiv. We've already seen this function before, and I'm going to reuse it here as an example. We define our type signature for the function as intDiv takes two ints and returns an either string int. When we ask GHCI for the type of the function, it responds with the exact same type, which is what you would expect. Now what happens when we ask GHCI for the type of a type? If we ask GHCI for the type of an int, we get an error saying the data constructor is not in scope. And if we ask GHCI for the type of either string int, it responds again with an error saying the either string and int data constructors are not in scope. It also tries to recommend an alternative in case you meant to use a variable with a similar name, either, that already has an existing binding. In our case, the recommendation is not useful. But why does this occur? If we look at what the GHCI help docs say, we can see that $t, which is actually just short for $type, takes an expression and shows the type of that expression. Remember, expressions are formed by using the data constructors, and that is why we get these data constructors not in scope errors, because Haskell cannot find a data constructor by the name of int or either or string. That is because those are not data constructors, but type constructors. But conceptually, just like how we can ask for the type of a data constructor, we should be able to ask for the type of a type constructor. Is there such a thing as the type of a type? That is where kinds come in. You can think of a kind as the type of a type. And just like there is a GHCI command for asking for the type of an expression, there is also a GHCI command for asking for the kind of a type. We can use the :kind command and pass a type to do this. Alternatively, we can use :k for short, as we will see. The response returned by GHCI when we ask it for a kind of a type can be confusing. Let's ask GHCI for the kind of an int. And we get told that the kind of an int is a star. What exactly is this star? Well, a star represents a concrete type. That is a type which is fully formed. In other words, it does not have any type parameters. Similarly, for a string, the kind is a star. Again, because a string does not have any type parameters. Now let's look at the kind for the maybe type. But before we do that, let's remind ourselves of the type definition. Unlike an int or a string, the maybe type has a type parameter a, and so you would expect its kind to be slightly different. When we look at the kind of the maybe type, things get interesting. We now have a kind of star to star. What does this mean? Remember, a star means a concrete type, a type which does not take a parameter. So the maybe kind takes a concrete type and returns a concrete type. The concrete type returned will be the maybe itself. The star syntax may seem weird at first, but once it's been explained, it should make sense, like for the maybe case. Finally, let's look at the either type. As a reminder, here is the definition of the either type. It takes two type parameters, which it calls a and b. Can you guess what the kind of the either type is? Well, since it takes two type parameters, its kind is star, arrow star, arrow star. The first star represents the A type parameter, the second star represents the B type parameter, and the final star represents the concrete type which is returned. This look into kinds is a detour and slightly beyond what a beginner needs to know, but I thought we should definitely cover it, so, like I said before, you can get a better understanding of the Haskell type system. And now we move on to an extremely important topic, type classes. Before I show you exactly what they are, let's consider the motivation behind them. Suppose we create our own data type called myBool, with two data constructors, t and f, representing true and false respectively. We are using these names to avoid clashing with the inbuilt ones which are already part of the Haskell Prelude. Now suppose that we want to write a function which shows a string representation of a myBool instance, which we will call showMyBool. The type signature of showMyBool would be myBool to string. And the implementation is quite simple. We provide two bindings for the function, one for each possible value in the pattern match, and return true if the value is t and false if the value is f. And the function works as we would expect. Now suppose we create another data type for representing certain errors which can occur in our program. and we want a function which shows us a string representation of the data type. So we write our function called showMyError that gives us a string representation for each of the potential values. There is nothing complicated here, we just use pattern matching to match on each constructor and return the description of the error as a string. And it works just as we would expect. Now, it is quite annoying to have to use a function with a different name for each type. Is there a way to generalize the ability to generate a string representation of a type to avoid this? At first, you might think, okay, maybe we can write a function which takes in any type and returns a string. In other languages, you can actually inspect the type of a value at runtime. But in Haskell, this is not possible. There is no way we can know what the caller of the function has decided to use as the type of the parameter at runtime, because at compile time, all we know is that it is of type A, and at runtime, there is no type information we can query. With this function signature, we must write our code for the most generic situation possible, and so it is not possible to write a function with this type signature and specialize it to act differently when the type of parameter is a myBool or a myError. But Haskell offers us another way of expressing that a type should be able to support a specific behavior, and that is through type classes. Type classes provide a structured way to introduce overloaded functions. We'll see what this means concretely in a minute, but in simple terms, function overloading is the ability to create multiple functions of the same name with different implementations depending on the types. That sounds like exactly what we need to define a generic myShow function. Let's use type classes to do that. There are two key concepts you need to understand when it comes to type classes. The first concept is the type class definition. The generic template for defining a type class is as follows. And here is our definition of the myShow type class. Let's take some time to understand what exactly we are doing here. You use the class keyword to declare a new type class. This is followed by the name of the type class which you want. In our case, we are defining our myShow type class. Then there is a type parameter which we conventionally call A. Then the where keyword, followed by a list of function signatures which can be overloaded. You can put as many function signatures as you want, but for our example, we are just putting one. Notice how the function signature is the same as the generic one we tried to define earlier. Now the second part of type classes is actually defining the overloaded functions. This is known as defining the instance for a type, and is done as follows. Here, the syntax is similar to the type class syntax we see above. We begin with the keyword instance instead of class, and then give the name of the type class followed by a value for the type parameter. In this case, the value is the myBool type. Then we have the where keyword, and in the where block below, we provide an implementation of the function specified in the type class. In our case, the only function specified in the type class is myShow. However, since we have provided the value of myBool for the type parameter A in our instance declaration, it is as if the function we are implementing has the type signature of myBool to string, and so we can implement the function just as we implemented our showMyBool function. You can see that the actual implementations here are identical, and we can create our instance for the myError type too. Just like before, it follows the same pattern. In this case, since the value given to the type parameter is myError, you can think of the function implementation in the where block having the type signature of myError to string. And so, we can provide the overloaded function definition which matches the exact same definition of the showMyError function which we defined before. You should note that the class and instance declarations follow the same whitespace rules we have gotten used to. After the where keyword, you should indent each line by the same amount of spaces, like you can see on the slide. What exactly does defining the myShow type class and also defining the myBool and myError instances for the type class give us? We can see what it gives us immediately by asking GHCI for the type of the myShow function, which is specified in the type class. If we do that, we get back a function signature like this, which contains a new notation. Just like before, we have the name of the function, which is myShow, followed by a double colon. But now we have the name of the type class myShow as well as the type parameter A, and then a different type of arrow symbol than we are used to. Then we have the actual type signature we specified in the type class definition. We call this new type of arrow a fat arrow, as opposed to the other thin arrow which we have already been using in our type signatures. Essentially, everything that comes between the double colon and the fat arrow is what we call a type class constraint. Sometimes it is called a type class restriction. We would read our generic myShow function signature as a function which takes in any type and returns a string. But with a type class constraint, we read this as a function which takes in any type which has an instance of the myShow type class and returns a string. Effectively, we are constraining the type parameter a to only belong to those types which have an instance for the myShow type class. This restriction means that we know that the type of the parameter passed in will have an overloaded definition of the myShow function which can be called. By having this type class constraint, we are able to overcome the problems associated with the generic myShow function, and whereas before we had to define a function with a different name for each different type, we are now able to just call the function with the same name, myShow, to get our results, which is much tidier. And when we do that, everything works fine, as you can see. But then what happens when we call it with another type? Let's suppose we call myShow with the value of true, which means we are calling it with the value of type bool. Well, we get an error, and this error occurs because Haskell cannot find any instance for the myShow type class for the bool type. We could get rid of this error by providing an instance of myShow bool, which would look very similar to our instance declaration for mybool. The good thing about this type of error is that it is picked up at compile time rather than at runtime, so you will have to fix it for you to even run your code. That's a lot we have covered in one slide, so let's summarize. A type class defines a set of function signatures that instances of the type class must implement. Within an instance declaration, the type parameter, which we conventionally call a, can be thought of as being filled with the concrete type given. So, for example, the type parameter a is given the value of mybool in the mybool instance declaration and the value of myError in the myError instance declaration. You can use type class constraints in your function signatures to restrict the type parameters to only be from those types which have instances of the specified type class. You can, if you need to, have more than one type parameter in a type class if you use a Haskell extension, but that is beyond the scope of this course, and we are only going to be looking at type classes with a single parameter. There is actually a type class predefined within Haskell called show that does exactly what our myShow type class does. The show type class is used everywhere, and we will look at it in more detail later. Haskell comes with a number of predefined type classes and instances. Some of the most used include the EQ type class, which you can use to define equality and inequality. So imagine you have two ints, a number 2 and a number 4, and you want to test if they are equal or not equal. Since int defines an instance for EQ, you are able to use the equals function and the not equal function. And because these are arithmetic operations, Haskell does some magic with these particular functions so that you can place them in the middle between the operands as you would expect. The show type class defines the show function that allows you to convert a value of a type to a string representation. In one of the previous slides, we created our own version, which we called myShow. I just did that as an illustration of type classes. In actual fact, we can just go ahead and use the inbuilt show type class and the show function to achieve the same thing. The inbuilt Haskell show type class includes some additional functions, show prec and show list. The prec stands for precedence. It's not important to understand these two additional functions since Haskell provides default implementations for them. We will cover default implementations in type classes later in this module. The bounded type class is used to define the upper and lower limits of a type. So, for example, we know with the int type that it has a min bound and a max bound, and we can see what it is because int defines an instance of the bounded type class. An int cannot store a value lower than the min bound or a value higher than the max bound. There is also a type class called ord for ordered types. Before we look at the function signatures, there is something different about this class declaration. This type class definition has a type class constraint in it. What this means is that any type which wants to define an instance of ORD must also have an instance of the EQ type class defined for it. So, in addition to the functions compare, less than or equal to, etc., the type also needs to have defined implementations for equals and not equals. This is how we can build up type class hierarchies. An int defines an instance for ORD, and we can see the usage of the functions in the type class here. When we compare 1 with 5, we get a value of LT back, which is an ordering. LT here means less than, because 1 is less than 5. When we test if 1 is less than 5, it is obviously true, and we get the expected results for the rest of the function calls as well. Now I'm not going to show the definitions for all of the inbuilt type classes, but there are some key additional ones which you should know about. The read type class is essentially the opposite of show, whereas show takes a value and returns its string representation, read takes a string and returns its value representation. The enum type class defines operations on sequentially ordered types. So since an int defines an instance for this type class, I can ask for the successor of a value. So I could ask for the successor of 4 and get 5, and the successor of 5 and get 6, etc. There are also a number of different type classes which are defined to represent the different operations for different numeric types. All of these type classes form a hierarchy, which is visible in the image on the right. For each type class in the prelude, you can see which types in the prelude define an instance. So for example, for the EQ type class, all of the types defined in the prelude have an instance for it, except for the IO type and this weird type with the arrow. Just ignore that weird type for now. For the num type class, the int, integer, float and double types define an instance. We can also see the hierarchy quite clearly by following the arrows. So, for example, the ORD type class has the constraint that the type must also have an instance of the EQ type class. And so if we go to the deepest type class in this hierarchy, the real float, we can see that any type that defines an instance of a real float must also have defined an instance of real frac, and real, and ORD, and num, and EQ, and show, and floating, and fractional. So if you have a type which defines an instance of a real float, which in this case would be a float or double, then you can do all of the operations defined in that type class hierarchy. Let's take some time to specifically understand the numeric type classes in the hierarchy. We have a number of different types defined for us in the Haskell Prelude for dealing with numbers. These include int, integer, float, double, which we have discussed before. Each of these types define instances for different type classes in the type hierarchy. All of them define instances for num. So let's see what that means exactly. Here is the definition of num as defined by GHC. There are a number of things I want to highlight about this definition. Firstly, if we look at the type hierarchy, we can see that the Haskell specification states that the num type class has a constraint. Any type which defines an instance of num should also define an instance of EQ and show. But in the definition we see here, there is no type class constraint present. Well, that is because the folks implementing the Glasgow Haskell compiler are being a bit cheeky, and since about 2012 have decided not to follow the specification completely. They have their reasons, and if you want to know more, you can check out the links in the footer. But if we look at EQ and show in the type class hierarchy, we can see that all types except IO and the weird arrow type which I said we can ignore define instances. So even though the type class constraint is not present in the type class definition, the types that implement the num type class also implement the EQ and show type classes. I'll show you how you can make the constraint explicit later in the module and effectively work around this. But for now, in most cases, we can just go ahead and act like the constraint is present. The second thing I want to highlight is related to the function specifications in the type class. We are only going to focus on the simple arithmetic functions here. If you want to find out more about the other functions, check out the documentation for the num type class. When you look at the simple arithmetic functions, you see addition, subtraction, and multiplication. Where exactly is division, and why is it not here? Let's suppose that num did have a divide function specified, just like it does for addition, subtraction, and multiplication. Well then, the type signature would be specified like this. And when we define our instances for the different numeric types, it would change to be like this. So for the float instance, we would take two floats, divide the first by the second, and return a float containing the result. Nothing wrong here, everything would work as we would expect it to. We have the same situation for the instance for the double. We take two doubles and return a double result. Again, nothing wrong here. But what happens when we look at what the int and integer type signatures would be for their instances? Suppose we divide 1 by 2. Now the result is a half, which is obviously a fraction. This can be represented by a float or a double, but how would we represent a half using an int or an integer type? Well, you can't. The only way to always be able to return an int or an integer when doing division is to perform some sort of rounding. And it is not always clear what type of rounding would be best. So rather than answer that question, Haskell does not define divide for the num class. Instead, if you want to perform integer division, Haskell provides explicit functions which perform different types of rounding. Haskell actually defines the division function in the fractional type class, for which only float and double define instances, like you would expect. If you want to read more about the other functions in the type class, check out the documentation link in the footer. If you remember, in one of the initial modules, when we were just learning about Haskell types, I showed you this simple piece of code, which fails to compile and produces an error. At the time, I said we should just stick to using doubles for division, and that you would not be able to understand the error message until we covered type classes. Well, now that we have covered type classes and understood the type hierarchy, this error message should also be understandable. Divide is defined on the fractional type class, for which only float and double define instances. So when we provide an int, like what we are doing here, we get the error message, saying that there is no instance defined for the fractional type class for int. So we've come a long way since the beginning of our Haskell journey to be able to understand what was previously a very cryptic error message. If you actually want to do integer division, you can use the div function. Div has the polymorphic type signature of taking two values of type A and returning a value of type A, with A being constrained to types which define an integral type class instance. We know that int and integer have instances of integral, and so we can pass these types as arguments to the div function. The div function performs integer division truncated to negative infinity, so we get the result of 0, which is expected. Let's spend some time on an exercise. Here is a partial definition of the EQ type class, which you will need for the exercise, and here is a custom type called myBool, and it is your task to define an instance of EQ for the myBool type class. Since the EQ type class is a bit different and defines operators which are supposed to be used in the infix position in between arguments, here is an example partial implementation showing how you can define one of the entries of the equals function. Pause the video for a moment and try it yourself, then I will go through the solution with you. Well, how did you get on? Here is the implementation which I have written. The definition for the equals function is as you would expect. We just go through each combination of values and return either true or false, depending on whether the values are the same. For the not equals function, we take a shortcut and just call the equals function and then call not to turn it into the opposite. This leads us on to our next topic, default implementations. You can actually provide default implementations of functions when declaring a type class. And if we look at the rest of the definition of the EQ type class, we can see it in action. Here, we can see that not equals has a default implementation defined in terms of equals, and equals has a default implementation defined in terms of not equals. What that means is, when we go ahead and define our instance, we do not necessarily have to define a function implementation. We can just rely on the default implementation in the type class declaration itself. If we go ahead and define a function implementation, then our definition will override the default implementation. In this case, since the default implementations of the EQ type class are mutually dependent, we need to at least provide a custom implementation for one of the functions. And so only one explicit function implementation is actually needed. Since they are mutually dependent, if we don't override at least one of the functions, then we will get a warning when we try to compile. And then, if we try to use the default implementation, equals calls not equals, and not equals calls equals, in a loop until the program blows up and throws an exception. So we have to make sure to override at least one of the function definitions to avoid this. Default implementations are useful, and when you can define them, They can save you time, which otherwise would be spent repeating function definitions throughout multiple instance declarations. Defining instances for EQ for your types can quickly become cumbersome and annoying. In this case, the definition of the myBool type is simple, and so is the definition of the EQ instance for it, but you can imagine how a type which has 5 to 6 fields can quickly become unwieldy to write EQ instance declarations for. Also, the type of code you are writing is essentially boilerplate code. To check for equality, you just need to pattern match on each possible outcome and return true or false if they are equal or not equal. And so Haskell offers us a better way. We can actually ask the compiler to automatically derive instances of type classes for our custom types by adding a deriving clause to our type declarations. Here is an example where we are defining a type called myBool2. We add the deriving clause to the end of the declaration and instruct the compiler to generate instances for our type for the show and EQ type classes. And so now we can use the show and equals functions without having to write any specific implementation. The only classes in the prelude for which you can derive instances for are EQ, odd, enum, bounded, show, and read. Now, if you remember, in one of the previous modules, when we were just starting with Haskell, I mentioned that you should just take a leap of faith and add deriving show to all of your type declarations to avoid getting an error such as this. This error occurs when we try to see something in GHCI, in this case some parameter d1 which does not define an instance of show, and so GHCI does not know how to print it to the screen. The error message says no instance for show day, meaning the type day does not define an instance for show. The way we fixed this issue was by adding the deriving show clause to the type declaration for the day type. Then everything worked. Now we have come full circle and you can understand exactly what is happening. The deriving show clause is instructing the compiler to automatically derive an instance for the show type class for the day type. That way you don't have to write one yourself. And the instance of show defines a function which can take a value of type day and convert it to a string, which can then be printed on the screen by GHCI. It took a while, and I promised I would explain what was going on, and finally we have got there. Deriving type class instances for EQ and show is extremely common for your custom type definitions, and is a very handy feature that saves us having to write tons of boilerplate code. We know that polymorphism literally means of many forms. In Haskell, there are two main types of polymorphism that we deal with and that we have now seen. The first is parametric polymorphism. This is where we use abstract symbols which can be substituted for any type. For example, in the type signature of the FST function, we are using the symbols A and B to refer to any type. So given a two-tuple, the return type will always match the type of the first element in the tuple. And we can see that in action here, where the return type is a string, the first time we call it, and an int, the second. This is an example of parametric polymorphism. The second type is ad-hoc polymorphism. In this case, we have a common interface defined in the function signature, but each type has a different implementation. In other words, the polymorphic function does different things on different types. We have seen how this works throughout this module with type classes. You might see these terms being used in literature which you read, so I thought I would mention them here so you don't get confused and can understand the differences between them. Let's do an exercise and try to find the correct type class constraints for a number of functions Haskell has in its prelude. You don't have to define the implementation, just try to calculate what the type class constraints would be. For reference, here is the type class hierarchy which you may find handy to refer to. The first function is sum, which takes in a list of any type and returns that type. The idea is that it would return the sum of all items in the list. What should the type class constraint on the function be to make it the most generic possible? If you guessed num, then you are correct. The num type class has instances of int, integer, float and double, and so covers all of the relevant type of numbers we want to sum over. But why num over real? Real has instances for these types too, doesn't it? Well, because the real type class expects instances to be ordered, since it has a constraint that its type must implement the odd type class. This is an unnecessary constraint to put on our sum function, since we do not need arguments to be ordered to calculate the sum. The second function is maximum, which again takes in a list of any type and returns that type. What should the type class constraint on this function be? If you guessed odd, then you are correct. In the most general sense, the maximum can be found for not just numbers, but also for other types which have a natural ordering, such as for characters. By requiring that the type have an instance of the odd type class, we make sure that there is a clear way to compare items in the list, and so we can extract the maximum through comparisons. And now we have another function called product. This is supposed to calculate the product of all items in the list. What should its type constraint be? For the exact same reasons as for the sum function, the type constraint is num. And finally, we have the minimum function. What should its type class constraint be? Just like for maximum, its constraint is odd. I want to take a minute to explore another interesting thing which we can do with type class constraints. Let's look at this function. All it does is take in an int, and if it is 0, return a string which says it is 0. Otherwise, it returns a string saying not 0. If we try to compile it with this function signature, we end up getting a compilation error which looks like this. The error says that for the pattern match f of 0, it is unable to find the EQ type class from the signature. If you remember, I mentioned it before. The GHC compiler since version 7.4.1 no longer follows the Haskell language specification for the num type class. According to the hierarchy, this should work because num is a subclass of EQ, but in GHC that is not the case. To fix this, we can follow the suggestion given in the error message and add the EQA constraint to the function signature like this. Since all of the types which have instances for the num type class also have instances for the EQ type class, this works. In this case, we are adding more than one constraint to the signature. In fact, you can add as many constraints as you need. I wanted to be sure to show this to you before moving on. We've covered a lot in this module. We began by looking at parametric polymorphism and saw how we can use lowercase names, customarily a single character like A or B, to represent any type in our function signatures. Then we discussed kinds. We can think of a kind as the type of a type. And then we explored type classes and saw how we could define them along with instances of them for specific types. Afterwards, we saw the type class hierarchy that is present within the Prelude and specifically focused on exploring the numeric type classes. Then we looked at providing default implementations for functions within a type class as well as automatically deriving instances. We then compared the two main types of polymorphism which we have learned about, parametric and ad-hoc. Finally, we ended with some fun exercises to see how we can use type class constraints in function signatures. I hope you enjoyed this module on polymorphism and type classes. The next modules in the course will build on your knowledge further by covering other essential topics such as recursion and lists. See you there!